Students, physics class 12, electric potential. This is video number 1 of chapter electric potential. In this chapter, we read about concept of electric potential, what is electric potential, and the formula related to electric potential. So first, the definition is given: electric potential difference. Electric potential difference. Electric potential difference. What is electric potential difference? If we place any test charge, see this. If we place, this is uniform electric field. You know that this is uniform electric field. When we place any test charge in this uniform electric field like Q0 at point A, you know that as well as any test charge placed in the electric field, there is a force act on it. Since it is point charge having positive charge, that is why the force acting on in the direction of the electric field. If we left it free, then it moves in the direction of the electric field. Suppose after covering some distance, it reaches point B. It reaches point B. So when we take it again from point B to point A, we have to do work against the force acting on it. This work is called electric potential difference. The definition of electric potential difference is total work done by taking a unit test charge from one place to other place in an electric field is called electric potential difference between that point. If W is the work done by taking this charge from point B to point A, then the electric potential difference is VA minus VB is equal to W upon Q naught. VA minus VB is equal to W upon Q naught. Its unit is, if we take it from point B to point A, then we take VA minus VB. If we take it from point A to point B, then VB minus VA. A final point minus A. Since it is positive charge, that is why the potential difference is between final point and initial point. Its unit is Joule per Coulomb. And dimension is, the dimension of work is ML2 T minus 2. And the dimension of charge is AT. So ML2 T minus 2, T minus 3, A minus 1. This is the electric potential difference. Their unit and their dimension. And from electric potential difference, the next definition is electric potential. Electric potential means electric potential at a particular point. If one point, if in the electric field, if one point is at infinity, if one point is at infinity, then it is called electric potential. The definition of electric potential is the total work done by taking a unit test charge from infinity to any point in the electric field, either point B, either point A. It is denoted by only V. V is equal to W upon Q naught. This is the electric potential at a particular point, either VA, either VB. The total work done by taking a unit test charge from infinity to any point in the electric field is called electric potential. At that point, it is denoted by V is equal to W upon Q naught. The unit and dimension is same. It is a scalar quantity. Unit is Joule per Coulomb. Dimension Joule per Coulomb or volt. Unit and dimension is same. And electric potential is a scalar quantity because the work is happen in the formula of electric potential. That is why it is a vector. It is a scalar quantity. There is no direction of electric potential. Now, the importance of electric potential is the charge is always flow from higher potential to lower potential. You know that. Charge will always flow from higher potential to lower potential. If we take two different charge objects and connected them by the wire, then the charge is always flow from higher potential to lower potential unless their potential not be same. When their potential is same, there is no charge flow between them. If two objects having different charge but their potential is same, there is no transfer of charge between them. That is the importance of electric potential. one in battery, one part is negative, positive, and one part is negative. Due to the potential difference, when battery is charged, one terminal is positive, other terminal is negative. Positive terminal means positive potential, and negative terminal having negative potential. And there is a potential difference set up between them when battery is charged. And when it is connected to the external terminal, there is a charge flow in the wire due to the potential difference. It is continuously flow unless their potential not be same, but in external circuit the potential not be same. That is why the current is continuously flow, charge is continuously flow. Now come to next point is electric potential at any point due to point charge. Electric potential at any point due to point charge. Okay, electric potential at any point due to point charge. Suppose this is any point charge situated at point O in a medium whose dielectric constant is K, and we have to find out the electric potential at a distance r from it. So at point A, by the definition, total burden by taking a test charge from infinity to any point in the electric field. This point is in the electric field of this charge. So total, we take any test charge and it is taken from infinity to this point, but infinity distance is not confirmed. That is why we place a test charge Q naught at this point, and we do reverse process. Test charge at this point, so the force acted on it F is equal to 1 upon 4 pi epsilon naught K Q naught upon R square. Now when we take it a small distance from A to B at a small distance dr, then a small burden dW is equal to F into dr 1 upon 4 pi epsilon naught K Q naught upon R square dr. This is a small burden by taking this charge from point A to point B. Similarly, when we take this charge from point B to point A, then work is negative. dW is minus 1 upon 4 pi epsilon naught K Q naught upon R square dr. This is a small burden, and as well as the distance is increased, the force is changed. It means this is a variable force, and the burden by the variable force will always find out by the integration method. That is why we find out a small burden by taking this point B to point A, and total burden by taking this charge from infinity. This is infinity, from infinity to point A, B to A, and the total burden by taking this W is equal to integration of minus dW, integration of dW, formula minus 1 upon 4 pi epsilon naught Q naught upon R square dr, constant 1 upon 4 pi epsilon naught K Q naught, integration of R to power minus 2 dr, integrate that, minus 1 upon 4 pi epsilon naught K Q naught, integrate that, minus 1 upon R, and total burden by taking this charge from infinity to point A. So we take limit, infinity is a lower limit and point A is at a distance R from charge, R, infinity to R कर देंगे, that is lower limit, upper limit. That is the total burden by taking this charge from infinity to point A. The distance of this point from infinity is infinite, initial point. The distance of this point from point O is R, that is final point. Now when integrate is 1 upon R की power minus 2, integration minus 2 plus 1 upon minus 2 plus 1, minus R की power minus 1, so minus 1 upon R and infinite R. So when we minus plus 1 upon minus plus 1 upon 4 pi epsilon naught K Q naught, putting upon limit, minus 1 upon infinite, but 1 upon infinite is a 0, So the net total burden by taking this charge 1 upon 4 pi epsilon naught K Q naught upon R. This is the burden. So the electric potential at point A, V is equal to W upon Q. V is equal to W upon Q naught. W is 1 upon 4 pi epsilon naught Q naught upon R upon Q naught. Q naught cancel out. Potential is V is equal to final formula 1 upon 4 pi epsilon naught K Q upon R. And for air or vacuum, the value of K is 1. V is equal to 1 upon 4 pi epsilon naught Q upon R. This is the electric potential at point A. But when charge is positive, the potential is positive. When the charge is negative, potential is negative. In formula of the potential, we have to take the sign of charge. When positive charge, the potential is positive. When negative charge, the potential is negative. And when many charges are placed, and the net electric potential at any point due to many charge is the sum of the electric potential produced by all charges. Okay, V is equal to V1 plus V2 plus V3, but not sign, not direction. Now next point is electric relation between intensity of electric field and electric potential difference. Intensity of electric field and electric potential difference. Relation between, that is very important too. Relation between E and V. Electric potential difference. Suppose this is any uniform electric field in which any test charge is placed at point A, Q naught, as well as it is placed, there is a force act on it, F is equal to Q naught E. F is equal to Q naught E. This due to this force, suppose it displays at a small distance dr and reaches point B. So when we take it again from point B to point A, then we do work dW is equal to minus F into dr. We have to apply force against this. dW is equal to F is equal to minus Q naught E into dr. Okay, and dW upon Q naught is equal to minus E into dr, and dW upon Q naught, total work done by taking any test charge from one point to other point, is called electric potential difference. If the electric potential difference V and VB, A and V is dV, then dV is equal to dV is equal to dW upon Q naught. So we can take dV is equal to minus E into dr. So the value of E is equal to minus dV upon dr. This is the relation between intensity of electric field and electric potential difference. And dV upon dr is called potential gradient. The value of electric field at any point is equal to potential gradient. The difference of the potential with respect to the distance is called potential gradient. It is also equal to. This is the relation. When potential is given, when we differentiate it with respect to R, we get intensity of electric field. When electric field is given, we integrate it with respect to R, we get electric potential. So, and when when we place any charge in the electric field, there is a force act on it, and due to the force it is moved. That is why it is having kinetic energy. So the formula of the kinetic energy of charged particle in the electric field, formula of K, see, of K in electric field of charged particle. Suppose this is uniform electric field. Suppose this is uniform electric field in which any charge Q naught is placed at point A. As well as we place this, there is force act on it, F is equal to Q naught E. Due to this force, it moves, and if the mass of the charged particle is m, then the acceleration due to this force F is equal to K is equal to F upon m. F is Q naught E upon m. This is acceleration. If this acceleration is moved, suppose after covering distance d, it reaches point B and acquire velocity v. So the velocity by the second equation of motion, by the third equation of motion, A to B, v square is equal to u square plus 2as. V square, u square is 0, A is equal to Q naught E upon m, and S is D. That is V square. V square is equal to 2Q naught E upon m into D. Now the kinetic energy is K is equal to half mv square. Kinetic energy of charged particle, the basic formula K is equal to half mv square. Half m, mass is m, 2Q naught E into D upon m. M cancel out, 2 cancel out. K is equal to Q naught into E into D. E into D, if the potential difference between A and V is V, then E is equal to, you know that V upon D. For long distance, we can use E is equal to V upon D. V is equal to E into D. V is the potential difference, E into D. So the kinetic energy is Q naught into V. It is directly proportional to the potential difference. The kinetic energy of charged particle in the electric field is directly proportional to the potential difference. When potential is increased, kinetic energy of charged particle is increased. That is why when high voltage is come, the value of the current is increased in the circuit, because the charge moves faster than before. That is why. Okay. And with the kinetic energy, another definition is 1 electron volt. Electron volt is also the unit of kinetic energy. 1 electron volt. What is 1 electron volt? The kinetic energy acquired by an electron when it is given 1 volt is called 1 electron volt. 1 eV, 1 electron volt is equal to the kinetic energy acquired by the electron for 1 electron volt. When 1 volt is given to that is called 1 electron volt. So the value of 1 electron volt is K is equal to QV. Electron is, the charge of electron is 1.6 into 10 to the power minus 19, and voltage is 1. So the value of K is 1.6 into 10 to the power minus 19. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. Okay, this is electron volt. Now electric potential energy. Next point is electric potential energy. That is very important. Electric potential energy and equipotential surface. Electric potential energy, you know that same type of charge always repel each other, and opposite types of charge always attract each other. That is why when we take opposite type of charge away from each other, say, near to each other, and when we take same type of charge near to each other or opposite type of charge away from each other, we have to do work against the force of attraction or repulsion. This work is stored in the charge in form of potential energy. That is called potential energy of the system. Suppose to charge potential energy. Formula of potential energy. Suppose to charge Q1 and Q2 are placed at a distance r from each other. We have to find out the potential energy of this system. So first we find out the potential at this point due to this charge. V is equal to 1 upon 4 pi epsilon naught Q upon R. Now the work done by taking this charge from infinity to point 1, V is equal to W upon Q2. Since Q2 charge is taken from infinity to point V, that is why the W is equal to V into Q2. That is W is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. This is the work, and this work is the potential energy of the system. U is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. That is the formula of potential energy. But in this formula, we have to take the sign of charge. When Q1 is negative, we have to take negative. When Q2 is positive, we have to take positive. And the other last definition is equipotential surface. Equipotential surface. What is equipotential surface? Equipotential surface. When we draw surface in the electric field in this type, that the potential at all point is same, that is called equipotential surface. When we draw any surface in the electric field in this type, that the potential at all point on the surface is same, that is called equipotential surface. Like this here, this is point charge, and when we take it is as a center and draw a sphere of definite radius, so this is equipotential surface. When the electric field, when ununiform electric field is happen, the equipotential surface is always spherical. Electric line of force is emerging. When we take it, when we find out that potential at any point, suppose the radius of this surface, spherical surface is r, so the potential at any point 1 upon 4 pi epsilon naught q upon r. So the potential at all point is same, that is equipotential surface. When electric field is uniform, equipotential surface is plane. When ununiform electric field is happen, the equipotential surface is spherical. When uniform electric field is happen, the spherical surface is plane. That is equipotential surface. And the property of equipotential surface, the potential at all point is same. When potential is at all point is same, there is no burden by taking any charge from one point to other point. Burden is zero. And the potential difference between 2 points is always zero. And the direction of electric line you are seeing the direction of electric line of force is always perpendicular to equipotential surface. Okay.